Question 15 is about differentiation. And we have to differentiate this rather awkward expression here. Okay, if we treat x plus y as a combined term, I get 3x plus y to the power 2. But now I have to differentiate with respect to x, remember, the inside. So differentiating x, this is simply 1. And differentiating y, well, it's going to be 1, but I must multiply this by dy dx because it's not the primary variable I'm differentiating to. And that is equal to, this is a straightforward differential, which is 6x. This differential, if I treat the y as an x, I get negative 3, but I must multiply by dy dx again. And the 2 differentiates to 0. So multiplying this bracket out, I get 3x plus y squared plus, and that's 3x plus y squared dy dx, is equal to 6x, and this minus 3 dy dx. So I can lose a factor of 3 throughout. So now I'm going to gather up all the terms with dy dx. So I'm saying dy dx, this is x plus y squared. This term moves across, becomes positive, so this is plus 1, close that bracket, equals everything else. We got 2x on that side, minus this term, which is x plus y squared. So therefore, dy dx is equal to the numerator, which is 2x minus x plus y squared, and this is divided by x plus y squared plus 1. And that should be the answer to part A. So we're now told that a point 0, 1 lies on C. Show that the normal to C at P has an equation of this. Okay, so to find the normal, we first need to find the gradient of the tangent. And we do that by subbing in x is equal to 1 and y is equal to 0 into our differential equation. So the gradient at P is equal to 2 minus x plus y, which is 1 squared, divided by, again 1 squared plus 1. And if you work this out, this is 2 minus 1, which is 1 over 2. So the gradient of the tangent is a half. So therefore gradient of normal is equal to negative 2. Now we can employ the gradient definition effectively and find the equation. So I get y minus the y value 0 over x minus 1 is equal to negative 2. Cross multiply. Y is equal to negative 2x positive 2. And that is what they've got up here. So bingo, that's the right answer. Now part C. Prove that the normal does not meet C again. You should use algebra and make your reasoning clear. Well, to do that, we've got to substitute the value of y as 2x plus 2 into our original equation up here and see what solutions we get. And prove also that we only get one solution. So substituting for y, I get negative x plus 2 cubed is equal to 3x squared. So I'm now multiplying y by negative 3. So this is positive 6x, take away 3 times 2, 6, negative 2. So multiplying 2 of the brackets out and simplifying the right hand side, I get this is x squared plus 4 minus 4x, and that's still going to be multiplied by negative x plus 2 is equal to 3x squared plus 6x minus 8. So therefore, multiplying this bracket by negative x, I get negative x cubed minus 4x plus 4x squared plus 2x squared plus 8 minus 8 x, and that is equal to the right hand side, which is 3x squared plus 6x minus 8. Pulling this all together, I get x cubed minus 3x squared plus 18x minus 16 is equal to 0. So as the point 1, 0 is the meeting of this curve and this line, I know that x minus 1 is a factor to this equation. So I can say that x minus 1 brought out must leave ax squared plus bx plus c as the multiplying quadratic. Now, equating the terms, I can immediately see that a must equal 1 and c must equal 16. And if I equate x squareds, I get that bx squared minus ax squared is equal to negative 3. And from that, I get the fact that b must equal negative 2. So my equation has turned into x minus 1, x squared, minus 2x plus 16. Now we test the discriminant, which is b squared minus 4ac, and see how many solutions this gives us. B squared minus 4ac will give us 4 minus 4 multiplied by 16, which is negative. And if the discriminant is negative, we know there are no solutions. So we know therefore there are no real solutions of this quadratic. So x minus 1 is the only solution for this equation. So therefore x is equal to 1 is the only meeting point. And that's the end of question 15.